Welcome to the Knowledge Graph seminar. Today, we are in the week 4 of the course, where our focus has been on how to create a knowledge graph from structured data. On Tuesday, we talked about some of the problems that arise in the process, including schema mapping, record linkage, and data cleaning. Today, we are very fortunate to have two experts on this topic. Lauren Orr, she is a postdoctoral fellow here at Stanford, and she is going to tell us about self-supervised entity disambiguation, which can further cut down the amount of human effort we have to invest during the data integration process. Mayank Kejriwal, he is a faculty member at the University of Southern California. He is also a co-author of a textbook on knowledge graphs, which has been recently released by MIT Press. He is going to tell us about entity resolution in web-scale knowledge graphs. And he's towards the end of his talk, he's also going to present a big picture vision of knowledge graphs and how these different steps fit in the overall process. So we are going to begin with Lauren telling us about self-supervised entity disambiguation. So Lauren, over to you.
Awesome. Thank you so much for the introduction. Let me make sure this, all right. Awesome. Can everyone see the slides okay?
Yes.
Awesome, great. All right, everyone. So my name is Laurel Orr. I'm a postdoc, obviously here at Stanford. I'm going to be talking about my work on self-supervised named entity disambiguation and our system, which we called Bootleg. And it's an amusing story how we came up with that name, and happy to chat more about it later. So as a primer, let me just explain what this task is. So this is the process of mapping from strings to things in a knowledge base. So for example, if you had the question, how tall is Lincoln? A personal assistant or the system would have to return that the mention is referring to Abraham Lincoln, not the car company or the city in Nebraska, to answer this question correctly. Now, this process of determining the entities that participate in text is a really key part of downstream applications like personal assistant, search, as I'll talk about later, relation extraction, and they're used by millions of people every day. So this really is a core pre-processing step to numerous downstream systems that you use all the time. Wait, okay, advance forward, okay. Here we go. Okay, so entities actually lie on a spectrum here, and this is something that we have broken up into 4 sort of subgroups, right? The very popular entities are what we call head entities, and these appear really frequently in your training data. And like Washington, D.C., for example, is a really popular entity. Everyone's very familiar with that. And you have a lot of textual data that you can train on to learn about what Washington, D.C. is. And this means that existing sort of information retrieval methods like BERT models are actually going to be able to do really well at disambiguating these entities. Now, on the other end of the spectrum, we have what we call tail and unseen entities that are seen very infrequently or not at all in your sort of standard training data sets, which I'll talk a little bit about later. So, for example, this song Sauce by an artist I'm not going to try to pronounce isn't even in the Wikidata knowledge graph, although it is in some sort of song database, and it's playable on Spotify, and people are going to want to ask their personal assistants to play this song. And so this rareness in training data is what makes this very difficult. Because you don't have a lot of textual context that you can use to resolve what this entity is, like what is the entity sauce. Now, why this is so important is that in industrial settings specifically, the majority of user queries are actually over these rare entities. And even if you look at sort of at Wikidata as a standard knowledge base, and then you have Wikipedia, which has textual information about entities, only about 13% of entities in Wikidata even appear in Wikipedia that you have textual information on. And even less than 1% of all songs and music brains are even in Wikidata, right? So you get this massive tail distribution of entities that don't have a lot of textual data that you can use. Now, why is this a challenge? Is that you can't really train traditional systems to disambiguate these rare entities. So standard baseline models for NED oftentimes use language models like BERT to perform disambiguation. And these models are going to basically memorize a lot of textual cues about an entity in order to know what the right answer is. And now you see over here on the right is you have a plot which is looking at the number of times an entity occurs approximately in training data versus its overall, a model's overall F1 accuracy. And we have this blue line, which is a standard language model based baseline. And what you can see here quite clearly is that once you start seeing an entity about 100 times in training is when the baseline language model is able to sort of do pretty well and get above around 60% F1. It's really over these rare things that it starts to struggle. Now, what this means is let's suppose you took one approach, which says, well, I want to use this baseline model and I want it to do at least 60% over all entities. What this means is that you'd have to scale your training data so that every entity was seen approximately 100 times. Now, there are 90 million entities approximately in Wikidata, and scaling that to have 100 occurrences of each entity is an infeasible amount of data to train on. So you really can't scale up your training data to get high coverage over the tail. That's really not an option. Now, we're going to show you how by using in our model bootleg, how we're able to achieve high performance over these rare entities by using these subtle reasoning patterns that you can use over the tail that do not rely on textual memorization, and how you can get about a 40 F1 point lift. And this is where, as you're going to see, where knowledge graph relationships and type information is going to come in to help us resolve entities over the tail. Awesome. Okay, so now the big question is how do you actually use these reasoning patterns to disambiguate the tail? So I'm going to give you a little bit of a primer and a high-level overview of how NED systems work, just so that you can understand the things I'm going to talk about next. Right, so the standard inputs outputs. You have an input, which is a sentence, like where is Lincoln in Logan County? And then the output of your model is going to be the entities that participate in the text. So in this case, you're going to have Lincoln, Illinois and Logan County, Illinois, rather than Lincoln, Nebraska, or some other Lincoln. So the first step in this process is where we actually extract candidates or candidate generation. I'm not going to talk about this a lot in detail, but the overall motivation for this is that it's very hard for a variety of reasons to sort of resolve against all entities in your knowledge base. And so usually there's a retrieval part to this pipeline where you limit the set of candidates to be those that are fairly relevant to the sentence and highly likely to be the answer. These candidates then, we extract what we call an entity profile. And this is basically information that's stored in a database, which is things like the entity type, unique identifier, and importantly, any structural metadata that you have that's associated with that entity, such as the entity type or the knowledge graph relationships that that entity is associated with. And I'll mention a little bit later how we actually extract this information in a self-supervised manner. So these payloads, or excuse me, these profiles get turned into entity payloads, which basically get fed into our neural model. And then our model is what's going to output the most likely entity for each mention that we extract in the sentence. So at a high level, this is sort of the inputs, outputs, and the data flow of an NED system. So now we're ready to dive into what's the most interesting part of this talk, which is these subtle reasoning cues that I hinted at earlier. So disambiguation requires information about individual entities, relationships, and types. Now I'm going to unpack this more with a couple examples. So if I asked you, where is Lincoln in Nebraska? Or what year did Steven Spielberg make Lincoln? You'd be able to know that the first Lincoln refers to Lincoln, Nebraska, the city, and that the latter refers to the movie Lincoln by Steven Spielberg. Now, the reason you do this is actually very straightforward, is because of the textual sort of patterns there. The movie Steven Spielberg is going to be highly associated, obviously, with the director or with Steven Spielberg, the textual phrase itself. And same thing with Lincoln. Lincoln is going to be highly associated with the word Nebraska. Now, these are patterns that can be memorized at the entity level. They're textual phrases that are associated with unique entities. Now, the challenge with these patterns is that they don't generalize. And by that, I mean, just because I've learned that Lincoln the movie is highly co-occurring with the phrase Steven Spielberg gives me no information about any other movies or any other things related to Lincoln or Steven Spielberg, right? It's unique to that entity itself. So this is a very useful and highly discriminative signal, meaning that it helps you really identify a unique entity, but it doesn't generalize, which means it's not going to help us over these rare entities that we don't see a lot. So another pattern is these knowledge graph relationships. So taking the sentence, David and Victoria Mitchell added spice to their marriage. Here, we actually know that there are two Victoria Mitchells that are actually in Wikipedia. One of them is a poker player and one of them is a runner. However, only one Victoria Mitchell is married to a David. And this is a comedian, David Mitchell. Now, the only way you're going to know what the right answer is by reasoning over the fact that these two, Victoria Mitchell and David Mitchell, are married. And that's going to help you resolve to the right David in this sentence. Now, the key thing here is that this information, knowledge about what a knowledge graph relationship is and what this means between entities is actually a generalizable signal. If I know what it means for two entities to be married, I can actually use that knowledge to resolve rare entities that are also married, even if I've never seen them before in training data. And this is the key to why reasoning over these structural patterns is going to help us. Now, another pattern is what we're calling type patterns. So for example, if you had the sentence, how tall is Lincoln? Obviously, that's going to refer to the person. What is the cheapest Lincoln is going to refer to the car company. And how many people are in Lincoln is going to refer to the location, right? And this is because different textual signals are associated actually with the type of an entity. People have heights, not car companies or locations, right? Car companies have prices, but not people or cities. And so these type patterns are going to also help us understand what the right entity is in the sentence. And again, this is another pattern that generalizes. If I know what it means to be a person and that people have heights, I can use this to resolve a rare person as well, even if I've never seen it before in training data. So again, these two signals of knowledge graphs and type patterns are really going to help us generalize and not necessarily need all this text memorization to understand the tail. And so these signals live in a hierarchy in terms of discrimination and generality. As I mentioned earlier, this text memorization pattern is highly discriminative. It helps you narrow down the entity a lot as to what the right answer is, but it's not general at all. Now, to motivate the rest of the hierarchy between the KG relationships and types, we did a little sort of examination of Wikipedia data and found that about 22% of entities have a relationship, and about 126 of these relationships occur more than 100 times. Now, what this means is, for one, we actually are going to see these relationships enough in sort of standard Wikipedia data in order to learn patterns over them. And it gives us a sense of how general this pattern is, as it only occurs 22% of the time compared to type patterns, which occur more frequently. The KG relationship is sort of in the middle of the hierarchy, and the type patterns are on the top. Now, the key takeaway of this last little section here is that the way that we're going to understand and disambiguate the tail is by teaching a model how to reason over type patterns and knowledge graph relationships. So now the next question is, how do you actually teach a model to do this? And our answer is actually all going to be through embeddings and a couple nice little tricks that we do to make this happen. Okay, so this is our overall sort of input output of the model. And I'm really going to just focus on this piece right here about looking at the entity payload and how our entities are formed, and then how our neural model uses those entities to perform disambiguation. So I'm just going to walk through what happens for a single entity candidate in our model. That's going to help understand how we do this disambiguation using types and relationships. So take here the candidate Logan County, Illinois, and its associated entity payload. The first step, the associated entity profile. So the first step in generating this entity payload, which is a representation of an entity, is we actually go ahead and we extract a unique embedding for every entity in a simple embedding matrix, which you can think of as like a key value store. So the key here is the unique entity ID, and the value is going to be its embedding its embedding representation. So you first extract this for every entity, for every unique entity. We then repeat the process for its relationships. So here you see that Logan County has a capital of relationship and a named after relationship. So I use those, query a similar embedding matrix that's over relations, and also add that to the payload. Now, critically, every entity that has a capital of relation is going to get the same embedding representation added to its payload. And this is the key to how we were able to allow signals to transfer from popular entities to rare entities. During training, I'm going to see a lot of popular entities, and some of these popular entities are going to have this capital of relationship. I'm going to learn signals over these popular entities associated with this relationship, and through this embedding, it's going to allow it to transfer to rare entities. And this again is the key insight that helps our model learn over these other signals. I repeat the process also for types, right? So the county gets a type and geographic location gets a type, and every single county is going to get the exact same type. Now, these simply get projected down and form what we're calling our entity representation or entity payload. And the key takeaway here is that I have an embedding for every layer of this signal hierarchy, which is going to allow our model to learn patterns over every single signal and store them in these embeddings. Okay, so now how are these actually used in a model for training? And so I'm going to go into a little bit of detail here, especially focusing on these KG patterns, because there's another trick that we do to allow the model to take advantage of knowledge graph relationships. And so we do keep our model somewhat standard in that we use transformer building blocks with a special sort of KG module on top. And so the basic workflow is you have these entity payload representations. And here on the left, you see the payload being generated again. And those representations get fed into our model along with a standard BERT-based sentence embedding. These get fed through two transformer architectures. One of them just helps you learn co-occurrence pattern between entities, and the other one helps you learn textual patterns between the entities and the sentence. Now, these output representations get merged together, and then we have this really special sort of KG module. And what this is it's allowing entities to transfer representations if they are connected in the knowledge graph directly. These representations then will get scored, and then we predict the most likely one. Now, why this is really interesting and important is that if you have a sentence, so take the sentence, Heidi and Seal live in Las Vegas. This was actually a sentence of a benchmark that we spent a lot of time thinking about. And so in this sentence, you have two people and that they're living in Las Vegas. Seal is actually a fairly unambiguous entity. There aren't many people named Seal who are in a knowledge base, and it actually refers to Seal, the singer. Heidi, however, is much more ambiguous. There are a lot of famous Heidis in Wikidata and in Wikipedia. So for a model, it's going to learn a representation for the entity Seal that's very highly scoring, right? It's fairly confident given the sentence that this is Seal the person. If this highly scoring representation can then transfer to Heidi, his wife, it's going to make Heidi also highly scoring because these two are connected in the knowledge graph. And this is what that KG module does, is it allows the model to reason over the fact that if I'm fairly certain that one entity is the right answer, it's also highly likely that another entity sharing a knowledge graph representation or relationship with that entity is also going to be the right answer. And so here is so this is our neural model. And again, it allows us to reason over all patterns. And again, has this little special KG module twist, which allows us to take further advantage of the knowledge graph relationships. Okay, so this is sort of the input output, our payloads and our neural model. And now I'm going to talk a little bit about how we do a couple little fancy training tricks and how we actually train our model. And there's two pieces to this. One of them is going to be a little bit of a fancy regularization trick, and another one is talking about our training data and how we can encourage the model to learn these signals using a technique that we're calling training set refinement. So what actually happens when you're really training these things in the real world is you'd love it for the model to be able to balance these signals appropriately on its own. Now, remember, as I said before, these signals are in a hierarchy, and that the entity signal, that blue embedding here in my model, is going to be the most discriminative signal. Now, models' tendencies when during training are to actually rely on this highly discriminative signal the most, which means if you don't do anything to prevent it, the model's basically going to rely most on this entity embedding, and it's not going to actually learn a lot over the relationships and types. Again, it's just natural tendency is to do the thing that helps it lower the loss the most, which is going to focus on the entity embedding. And so we really want to induct, to sort of add a sort of fancy ML term here, we want to have an inductive bias in the model that pushes it towards learning information in the relationships and types over this entity representation. Because again, the whole point is to learn better, is to have the model learn better things over the tail. However, we don't want it to totally ignore this entity embedding. It is going to encode a lot of useful information, especially for very popular entities that it sees a lot. So what we do is, it's fairly straightforward, is we actually regularize the entity embedding proportional to the inverse popularity. Now, what I mean by that is that with a probability proportional to the inverse of its popularity, which means the more popular the entity, the less likely it is to be regularized. And when we regularize it, we basically set all values in the embedding to 0. And this prevents the model from using any information or storing any information in that embedding, because it's all set to 0. So for very popular entities, this doesn't happen very frequently, and the model is going to store more information in that entity embedding, which is okay. That's what we want. Now, for rare entities, this is very likely going to be set to 0, and it's going to force the model to use relationships and types to perform disambiguation. Now, this simple trick of just regularizing the entity embedding gives us about 13.6 F1 points on these unseen entities. So this is a massive lift over these rare entities just by, again, forcing the model to store patterns in the right place. And this is, these are little tricks that you have to do, again, to encourage the model to do something that it is, that's going to be a little worse for its overall loss, but it's going to help you over the tail. Now, the last thing that I want to touch upon here is how we actually perform training and what we actually train on. And so again, our model is self-supervised, and this is something that we very strongly wanted to sort of maintain with our model, is that it was more hands-off. And by that, I mean, you didn't have to have engineers sort of manually curating features or labeling data. We wanted it to be very sort of automatic, or as automatic as possible. And so we had to find training data that was basically labeled for us, or that we could label automatically. And so it turns out, and this is a standard thing that any of these systems do, that Wikipedia has a lot of useful information in it. And importantly, Wikipedia has these things called interlinks. So if you're on a Wikipedia page and you see this text that's blue, you click on it and you go to another Wikipedia page. This is a user who sort of manually annotated this, and it actually forms training data that we can do for disambiguation. So in this sentence from Wikipedia, we have, although they toured together, Lincoln did not take its name from They Might Be Giants album Lincoln. And so here on Wikipedia, that Lincoln is linked, and it's pointing to Lincoln the band. Now, this is going to serve as a label for us for training. So basically, we train by reading Wikipedia, which is pretty exciting. And what we also do is we use a standard Wikidata to sort of extract the structural metadata and form those entity profiles that I talked about earlier. So we pre-process all of our data automatically by scraping Wikipedia, gathering the labels, and then gathering the structured data from Wikidata, all automatically stored and sort of a one-click process, so that there's no sort of manual interaction with this. And again, the huge takeaway here is that not only is it sort of easy for us to do, but it's a simpler, more straightforward pipeline when you're training these systems. Engineers don't have to sort of modify things manually, and it's very easy to extend to other languages. I just have to point my processing onto another language of Wikipedia. It does lead to some issues in that sometimes languages are resource poor, but that's a separate talk. Now, I did also mention that we can use a couple of tricks as well on the training data to help our model learn these rare patterns, or these structural patterns, more. Now, it turns out that Wikipedia is known to be actually fairly sparsely labeled and to be missing mentions. So in that sentence I showed you earlier about Lincoln, you actually see that they have a reference to Lincoln the album at the bottom of the sentence, which is clearly pointing to that entity, but that label, that mention isn't actually labeled in Wikipedia. And this is due a lot to an artifact of Wikipedia and sort of the standards that users take when they're labeling interlinks in Wikipedia. However, Wikipedia is also highly structured. Most of the time when you're on a Wikipedia page, a lot of mentions about that entity are referring to the page that you're on itself. And so we can actually use this to do some weak supervision-based techniques to label our data automatically to sort of increase our label coverage. And so here, for example, this means that we can use some standard sort of weak supervision methods to label the second mention of Lincoln to be pointing to Lincoln the album. Now, this simple heuristic, again, is it's weakly supervised. So again, we had to sort of work on writing some sort of heuristic labeling functions, but after that, it was all automatic. And now we increase our training data through this technique by about 1.7 times. And we also see a little bit of a lift on these unseen entities as well. And this is because when we add these extra labels, you're also going to be enhancing some of these signals more. So if I had a sentence, again, that was about Heidi and Seal living in Las Vegas, and only one of Heidi or Seal was labeled, if my weak labeling method labeled the other one, then that would give my model more access to these knowledge graph signals, for example. And so again, this is a very sort of simple technique that also helps our model improve performance over these rare entities. Okay, so I'm going to talk about a couple experiments here. And the first one is sort of the standard state-of-the-art benchmark experiment that all papers have nowadays, and just showing that our model performs very nicely over sort of standard NED benchmarks. But that's not actually really that interesting. The tail is really where things get interesting. And so here we have this Wikipedia data set, and we compare our model bootleg compared to a standard language model-based baseline that is also trained over the same data. And we see that over all entities, this baseline model is about 5 points away from bootleg. And I want to be very clear, we did not do a lot of tuning here. We kind of just clicked it and ran and sort of went with the result. So again, the performance could probably have been improved a little bit with a little sort of parameter tuning. However, it's really over the tail that you see a dramatic difference in performance, where over these unseen entities, this language model baseline is about 40 points beneath our bootleg model. And that's just because of these structural signals, right? Like this language model baseline just uses textual memorization to perform disambiguation, and it's really going to struggle over these rare entities. Now, another subtle point here, which is a lot of what our group's also working on, is that this overall evaluation set of F1, the all evaluation set here, is fairly misleading in that standard sort of development test sets also sometimes can be popular entity biased, which means you're not really seeing the true performance of your model using standard evaluation metrics. Now, to understand our performance lift and understanding where our gains were coming from, we ended up doing a little bit of a subpopulation sliced-based evaluation. So we mined for different subpopulations in the data where we thought the different reasoning patterns were present. So for example, if you had two entities that shared a knowledge graph relationship and that they were the correct entities in the sentence, we would go ahead and put that in our KG subpopulation bucket. And we did something similar for types, where we looked at entities that had commonly co-occurring textual patterns associated with the type of their entity. So for example, the word height appearing with a person. We put that in our type bucket. And then our entity bucket is anything that was basically not in a type or a KG bucket. And here again, we see that the bootleg performance is dramatically better over the tail and also over these reasoning pattern slices. We see here that again, for the type and the KG bucket, bootleg is dramatically better than this BERT baseline model by about 60 points, especially on this KG1 over the tail. And again, this is really demonstrating that our model, it's in these reasoning patterns that we're able to sort of boost performance. Now the last, I'm going to skip over this one. The last one I want to talk about, which I think is a really interesting downstream task that we explored, is we also wanted to understand, as I said earlier, entity embeddings are very useful in that because of the downstream systems that you can use them in. And so what we did is we took a standard relation extraction benchmark where, given a sentence, as you see on the slide, and a subject and object, The goal is to predict the relationship between them. So in this case, Maze is an employee of Media Enterprises, and you want the model to be able to predict that. What we did is we took a standard baseline model. Well, at the time, it was a close to state-of-the-art model called SpanBERT. We compared it to a model that also had some entity knowledge incorporated in it called NoBERT. And then we also added our own bootleg embeddings to the SpanBERT model and sort of compared comparison here. And we set a new state-of-the-art on this relation extractor benchmark just by adding bootleg embeddings. But the really interesting part is why. So when you actually break down and try to see what our model got right that the other model got wrong, is you start to see where these knowledge graph and type cues and entity cues can be really helpful. So here our model was able to correctly predict that these two entities had the relationship cause of death because they were actually linked in our knowledge graph. Bootleg predicted these two entities and indicated to us that this was the relationship between them. And we were able to get that correct because of it. We also were able to get things correct because we're able to correctly perform disambiguation and resolve the same entity, and we're able to capture relationships such as alternate names. Yeah, so this is a very exciting thing. And another subtle point here is that you could actually conceivably use bootleg to mine for more relationships that can go into your knowledge graph. So it can actually form sort of a cycle of information because you're extracting relationships, which is just extracting other triples that are in your knowledge graph. So kind of a nice little sort of closed loop cycle there. All right, so this is sort of the overview of bootleg. Our goal was to make it a sort of tail focused NED system, and it's also open source. So please check out our link below and our website for more information. Yeah, take a look. And the key ideas again are leveraging these patterns over types and knowledge graph relationships to improve performance over the tail. And we also had some work in a paper which was talking about patching errors, which is why that last comment's in there. Yeah, so thank you so much for letting me sort of give a little bit of a talk, and yeah, I'll taking questions now or later, whatever.
At the end, yeah, we'll have about 20 minutes at the end for questions.
Awesome, perfect.
Yeah. Thanks, Laura.
Thank you so much.
Yeah. I mean, you've done very interesting work, but I also love the logo that you have.
Yeah. No, that was a friend of mine and I were sitting in our office. I don't even, we talk, so cocktails are actually a really common thing that you struggle to disambiguate because you'll have cocktails like champagne, Manhattan, Boston, things like that, which are oftentimes named after locations. And so we had this cocktail theme going on, and then talked about a bootlegger, which is someone who can like smuggle things like alcohol, and anyway, turned into some cat smuggling things around. So yeah,
it's a little bit of Pirates of Caribbean feel also.
Yeah, definitely. We enjoyed that.
All right, so we will move on to our second presentation. Mayank, over to you.
All right, thank you. All right, you still see my screen, right? Let me go to full screen. All right, I'm gonna make sure I keep a lid on time. All right, so I'm Mayank. I'm very happy to be here today. Thank you for inviting me. And today I want to talk about what is really a vision, I think, and has been a community level vision for the last 15 years, which is, how to do entity resolution on web knowledge graphs. And I'll say a little bit about why this is a vision, especially for the web, and why it's proven to be hard, and where we are right now and where we're going next. So a little bit about me. So I'm a faculty at USC in the Department of Industrial and Systems Engineering, and also have a joint appointment in the Information Sciences Institute. And we work on a lot of different projects. So here's a snapshot of some of my projects. So I do a lot of work in AI for social good, and almost all of these knowledge graphs are heavily applied. So it's always fantastic to see a course like this being offered. And in fact, on the common sense reasoning, this project, we work with Yuri Leskovich over at Stanford CS. So we have a small connection over here to you guys, and these are all very exciting applications of knowledge graphs. Okay, so, and by the way, if you're interested in any of those projects, you want to learn more about any of those projects, feel free to ask me or reach out to me. I love to connect over them. All right, so let me begin with an observation before I actually get into the problem. And the observation that I always like to begin with is that, if you think about it, we are moving from a web of linked documents. So this is what we think of the web as being traditionally, right? That you have these hyperlinked documents, and HTML pages and so on. But we are actually moving from that to a web of linked data. Now, that does not mean that this is replacing the web of documents. This is existing along with the web of documents. But we are datafying a lot of the information that is on the web. The Google Knowledge Graph, of course, is a very good example of that. But even before the Google Knowledge Graph in 2011, we already had a movement underway called linked open data. So this is just a visual of linked open data in the mid 2010s. In 2007, linked open data just started with 12 RDF data sets. I'll go a little bit into what RDF is, but you can just think of it as a knowledge graph model. And it grew very fast. In just 10 years, it went from 12 small data sets, relatively small data sets, to more than 1,000 data sets with millions of nodes between them. It was linked to documents. There were actual pieces of data. There were URIs and lots and lots of different things, lots of different domains also. So everything from media to publications to what we call cross-domain data sets, which are things like DBpedia, which is extracted from Wikipedia, Freebase, which was bought by Google and was built upon for Google Knowledge Graph, social networking, life sciences, and many others. By the way, if you're very interested in this, I highly recommend a 2001 paper that was published in Scientific American by Tim Berners-Lee, the inventor of the World Wide Web, where he laid out a vision for what he called the semantic web. And this is sort of a very central movement in the semantic web. So highly encourage reading that very accessible article on the vision from going from the web of documents to the web of data, all the way back to 2001. So what is linked data? It turns out it's not actually data. Linked data is a set of 4 best practices for publishing and connecting structured data on the web. So this is a very simple definition. And of course, the data sets that we actually publish using these principles is sometimes also referred to as linked data or as linked open data, as I showed in the previous slide. I won't go into all the best practices, but one of the best practices is that whenever you publish data on the web, you have to connect it to existing data sets. And this might seem like common sense, right? If you're publishing something on the web, you should actually provide links to other things. But it turns out that if there are many people who like to extract from their data set, they publish it on the web and they forget to link it to existing data on the web. So you have to make a very strong effort to link your data set to other data sets on the web. And that's why it's a best practice. And that's where the linked and linked data comes from. Now, I also want to introduce my running example, which I will use throughout the talk. And on the left-hand side, you have Freebase in orange. And it's a very intuitive example. You have Microsoft. Microsoft was co-founded by Paul Allen, one of the co-founders. Microsoft is a firm. A firm is a type of organization, and so on and so forth. On the other side, you have DBpedia, where you also have Paul Allen. But you can see that there are differences between the two knowledge graphs. And some of the differences seem very evident, but others are more subtle. Like you have inventor over here, an entrepreneur over here. You have non-profit over here, but there's nothing over here that seems to resemble a non-profit, right? And so just keep this example in mind. We will go over it in a lot of detail. You will see that the example expresses a lot of the problems that we often see on the web. Before I go deeper into what's wrong with this, I do want to introduce RDF because it's a very important model, especially in our community, the semantic web. And an RDF, which stands for Resource Description Framework, is a very simple model definitionally. So an RDF dataset is a set of triples. The triples can be visualized as a directed labeled graph. So every edge in this graph is a triple, right? So you have the head entity, relation, tail entity. We've seen that concept being introduced already. but there is, not every triple can actually meet the definition of an RDF triple. So there's a very specific format that you must obey when you have an RDF graph. And what that format is that the subject, what we call the subject or the head entity, must be a URI or a uniform resource identifier. The property must also be a URI. The object may be a URI or a literal. A literal is a primitive data type. It could be a string, it could be a number. It could, it's just think of it that way. There is a more formal definition. But the important thing is the subject and the property or the predicate must be URIs. The object may be a URI or a literal. Now, because this data model was designed for the web, in fact, the W3C, the World Wide Web Consortium, which is a very influential body that comes out with recommendations for the web and specifications for the web, has a full specification on RDF, because this is a data model that is really designed to publish KGs on the web. And in practice, many of the URIs are URLs. So when you click on a resource, when you click on the subject or the property, it will take you to a web page that describes the URL. So you can now see how the connection starts becoming more explicit between a knowledge graph and the documents that underlie the knowledge graphs. And in fact, one of the linked data practices is that you should try to publish your KGs in a standard format, such as RDF. So just wanted to give that little bit of background on why this notation is here. Freebase over here, when you see a notation like this, where you have freebase and a colon, and then a sort of a very specific kind of string, this is usually a prefix, so it might stand for freebase.com, and the colon is slash, and so all it means, this is like a shorthand way of representing a URL. And I encourage you to read a lot about RDF on w3.org, especially if you work with KGs over the web. You'll find that it's very useful for understanding KGs at web scale. So what is entity resolution? Simply put, it is the algorithmic problem of connecting pairs of entities that refer to the same underlying entity. We've already seen some examples here, right? So you have Microsoft, which is the same as Microsoft Corp in DBpedia. You have Paul G. Allen, which is the same as Paul Allen in DBpedia. And one of the really nice things about the semantic web is that we have a predicate called same as, and there are some equivalents of this also. But the same as predicate, you can just declare a triple between two resources, right? So you have like Freebase Microsoft subject same as DBpedia Microsoft Corp, and that's a triple. And it's understood that when you define same as, it's symmetric. So when this Microsoft is the same as this Microsoft, then by symmetry, Microsoft Corp is the same as Microsoft. And so this is the kind of thing that happens in a reasoning engine, where if you have if you look up Protege, it was created by another group at Stanford, and I highly encourage you to look that up as well. It's an open source. It's a package that you can use to work with ontologies, and with these kind of same as assertions and so on. It has reasoning. It has support for reasoning built in. So again, a very useful tool that is prominent in the semantic web and has a deep connection to a group at Stanford. But the idea here is that this model, the RDF model, can really be used to represent the same as links between different data sets. You can also have this problem in the same data set. So a lot of times when you have a very noisy data set, the same problem might occur within the single data set. The same theory applies, especially when you have a simple model like RDF. But as we will see, when you have two different data sets, which is what we see on the web, right? When you're trying to link all these different data sets together, described in different ways, the problem does become a little bit harder than when you're just dealing with one data set and you're trying to link things within one data set. Now, one of the ironies about entity resolution is that when you look in the literature, the name entity resolution itself suffers from entity resolution. So you will see instance matching, entity matching, co-reference resolution, which is really more of an NLP version of the problem, merge purge, record linkage, which is more of a database level problem, deduplication. I mean, there's just a soup of terminologies out there. They are not different problems. They are very similar. They just have slightly different sub-communities, slightly different publication venues, but they are really all one and the same problem at a very fundamental level, which is connecting pairs of entities that refer to the same underlying entity. Now, why do we want to do this? And so this is something that you won't find in a book. So I want to introduce this problem to you so that you can really think big about this if you try to do this. Now, for those of you who are familiar with the internet, right, we have this thing called the DNS, which is really an addressing system for the internet. It's one of the things that makes the internet possible, right? What we want to do as a community, and what I am very interested in as a researcher, is a higher level concept called the ENS. So the ENS, the entity name system, is trying to do for entities that are getting published on the web, whether it's through knowledge graphs like Wikidata and DBpedia and many other knowledge graphs. But we want to populate an ENS, and the inspiration is taken from the DNS, right? So imagine that instead of having so many different Paul Allens, you only had one Paul Allen, right? And that one Paul Allen is linked to all the different Paul Allens all over the web. And imagine if we could have a web like that, right? Now, we're not getting rid of the other Paul Allens. We are encouraging you to publish your own Paul Allen. Maybe you have extra information about Paul Allen. Paul Allen might have has a social networking website where he puts tweets and etc. So there's still a lot of control and decentralization of individual publishers. But what we would really like to do is link all of these things to the single Paul Allen in the ENS so that you can really start to see the web as a global database, right? And if we can do that, and that's really the vision that Tim Berners-Lee also has, it just unlocks all kinds of applications, right? So that's the big vision. If you can do this, then you can start unlocking all kinds of applications, sort of like Amazon has done for e-commerce. Now, of course, that brings us to the question that how do we do this, right? So if we want to do this, is this just a pie in the sky idea? Or can we identify specific requirements that if we can fulfill those requirements, we can start to do this? This is also very important because it gives us a roadmap, that if we can identify those requirements, then we can start measuring progress on those requirements. And that helps us to get closer to the vision. So this is the question that I started thinking about when I began my PhD, which was sort of in the early 2010s. So my advisor told me that, you should really start with a question like this and just go out, read hundreds of papers, see what everyone is trying to do, and then, try to analyze and synthesize all of that, almost like a survey paper, to figure out what the requirements are, and then pitch that to the community, argue that to the community, and then start solving it. And maybe you won't end up solving the problem within your PhD, but you'll solve enough that other people can then build on top of you, and you can then go on in your academic career and start building on top of that. So for the PhD students out there, I think it's helpful to start with a big question and then to go from the big question into the more narrower, doable segments, that can feed into the big question. So let's return to our example, to start thinking about how I came up with those requirements. I want to take you through my thinking process very briefly. And what I saw in this example, the first thing that I noticed is, that the two data sets are very heterogeneous at the metadata level, right? So there are two different kinds of heterogeneity that I identified. One of them is type heterogeneity, right? So in one data set, you have firm and organization and nonprofit. In the other one, you have company, inventor, and person, right? So this is an illustrative example. But now, if you think about a full ontology with all the types in it and subtypes, there's a mismatch between many ontologies and schemas that are used. And in one of the future talks, hopefully you will hear about schema matching. So you'll learn a lot more about what makes that problem challenging. But we need to match these types in some ways, right? And sometimes it's not a one-to-one match. It's more like a subset or a superset match. So we have to keep that in mind. The other kind of heterogeneity is property heterogeneity, right? So we have co-founder of over here, but over here we have things like organization, right? So Paul Allen belongs to Microsoft through the organization property, but here we have co-founder of. Clearly there is some kind of semantic match between these two, even though they may not be identical. We need to see more examples before we know what this really means, right? Like, does this mean that you belong to the organization? So even employees would be connected to Microsoft Corp through this predicate? Or does it mean that you're a co-founder and that's the real meaning, even though it doesn't come across in the string meaning, right? So what's the practical semantics of the property? So we also need to have some kind of understanding of that. Now, even if we do that, there are two other problems which only come across when you look at the higher level picture. One of those problems, if you want to do this at web scale, is domain independence, right? So we have so many different domains over here. And it's easy to think that cross domains actually provide something that you can use to train everything. It turns out that there are many domains where there's almost no overlap with the cross domain data set, like Wikipedia or DBpedia. I think the easiest example is a publication data set, right? You have these big publication data sets like are owned by Google Scholar. You have the Scopus, you have the Semantic Scholar that is maintained by the Allen Institute, and so on. Some of the influential papers might be linked to Wikipedia, but not all. We have millions of papers. Not every paper has a link to Wikipedia. Not every scientist has a Wikipedia page. I don't have a Wikipedia page. I'm not that famous. And so on and so forth. So there are lots and lots of things for which you don't have an entity in some of these knowledge graphs, right? And the long tail problem is also there, as we saw before. So, you want to do this for any pair of any domain. You don't want to train something for one domain or even just for cross domain, but you want domain independence. And that brings me to the second problem, which is automation. You want things to be relatively automated. One of the stories that I want to tell you, or not really a story, but it turns out that a lot of people outside computer science often ask the question, well, why do you want to automate everything? And that is a good question, right? We seem to take it for granted in AI that everything should be automated. But it turns out that this is getting a lot of pushback now from both within AI and outside of AI, where the thought is, well, if I can train a big enough data set, or a big enough set of labels, and I can train and I can get a system that is seemingly automated, right? But then we move it to a different domain and we might have a problem. Also, who's going to give us those labels, right? Like, is everything, do we just do we use distant supervision, get something from the web? Do we need to use crowdsourced workers? Do we use one of the startups that does data labeling for you at a cost? Like, what do we do? Data labeling is manual effort, right? Even though it might lead to what we might call an automated system. So we need automation because we certainly can't label everything over here, right? And we don't want to spend too much time labeling anything if we can help it. So we want to minimize manual effort. Ultimately, if you want to do this at scale, if anyone wants to do this, you publish the data set, it links to every other data set or most data sets on here. It has to be automated. Otherwise, it's not feasible. It will not scale with the web. So in other words, the hypothesis was that if you want to populate a linked data ENS, you need to simultaneously, and the word simultaneous is very important here, fulfill the 4 dash requirements. We call these the dash requirements of domain independence, automation, scalability, and the 2 kinds of heterogeneity that I identified, type and property. Now, simultaneous is important because even though I won't have time to go into it in this talk, it turns out when you look at the literature, and I go in depth into this in my thesis, which was published in 2016, that you can find many papers that are fulfilling 1 requirement, sometimes 2, but we could not find a paper that was dealing with 3 of them, let alone all 4 of them, the way that we defined it. And we gave very precise definitions along the lines that I just told you about, but it's very difficult to find a system that can deal with all 4. And there are very real trade-offs that, if you want to deal with automation and with domain independence, and scalability might be a problem because many of these automated systems are very complex. They have complex optimization functions. They have to iterate a lot. And how do we do that if we're trying to scale? Like, can we do this in a MapReduce architecture or a Spark architecture when we're dealing with many millions of nodes, right? So web scale scalability can be difficult to reconcile with something like automation. We also want to do this in a way so that we can deal with noise, because nothing is going to be noiseless, right? So how do we do it in a way that we have a acceptable quality, not perfect, but acceptable? So, let me walk you through some of the steps that we need to take to deal with this. the first step is really to do type alignment, right? So we need to match entrepreneur with inventor and company with firm. And there are going to be many, many types. And if you go across domains, you might have biological types, you might have, all kinds of other types that we would not be able to understand in a common sense fashion. But we need to do that somehow. It turns out there are unsupervised methods for doing this. And they are based on the entities that are covered by the types. You can sort of think about, you can use an embedding based approach, you can use clustering of the embeddings to figure out which types are practically the same, even though the string semantics may not be the same. But this is the first step. We first need to identify what are the types, because that is the highest granularity, that is the coarsest granularity at which you need to do the matching. Next, within each pair of matching types, we need to identify the predicates that are matching. Now, I'm not putting same as over here. Notice I'm not putting same as, because they may not be same as. The best that we may be able to do is to say that there is some kind of relationship between these two predicates, but we can't say they're identical. Sometimes they are, but at other times, it might be that one is a subset or one is overlapping with the other. So in a higher level system, you not only want to align them, but you also want to assign semantics to the alignment. Is it just overlap? Is it subset? Is it superset? What is it? So it turns out that's a hard problem, hasn't been explored as much in the KG community. Now, let's say we do all of that, all right? Is it enough to just compute the set of nodes that have a certain type and the set of nodes that have a certain type, and then just do a pairwise comparison? It turns out you can't do that if you want to be scalable. And the reason is, if you have n nodes over here and you have m nodes over here, then you're looking at O of mn comparisons. You go into the tens of thousands, and now all of a sudden we are talking about hundreds of millions of comparisons. That is clearly not feasible, and we're dealing with KGs that are much bigger than 10,000 nodes, and and so on. So we need to do something more, and this something more is called blocking. This is a very age-old technique. It has been around for decades, especially in the database community. And what this means is that you apply a function. Think of it almost like a hash. There's a hash. For example, let's say you tokenize the last name in a customer data set. And based on that, you can now hash things to these blocks, which may overlap, because my last name may have two names. I may have a double token in my last name. And so I might get hashed to two blocks. That's fine. And then we only link, we only compute the expensive, the similarity function, which could be any expensive. It could be very expensive and use all kinds of string similarity and all kinds of expensive things between nodes that belong to the same block, right? And so you can see, even in this very simple example, we've gone from 24 pairs to something like 7 or 8 pairs. And usually, we can go from O of mn to something like O of n plus n. So suddenly it becomes feasible. You can deal with million node knowledge graphs because you're not dealing with trillions of comparisons anymore. But how do you get a good blocking key, right? And how do you get a good similarity function? So these are all interesting problems. And then finally, your final output is you do all of that, and then you get the same as links, and then you put them in the ENS, and you have entity resolution at the web scale, right? So that's the vision, at least. But it turns out that when we went into this, what we really found was this, so there was a supervised way of dealing with some of these problems. No one had put everything together. So we had to first put everything together, even just to put together a baseline. And the idea was that, okay, you give a training set of duplicates and non-duplicates. You can learn a property alignment. We're not dealing with class alignment in this. There's a separate algorithm for that. And then you learn the blocking key, you learn the similarity function, you get the two knowledge graphs, you execute the blocking and similarity, and you get the same as. But it requires this training set, which can be problematic, right? The moment you change your data sets, let alone the domains. Now, after that, as we moved along, what we did was that we tried to innovate step by step, while still maintaining the 4 requirements. We wanted to move towards the 4 simultaneous requirements by first starting with this baseline and then gradually moving up. So, for example, we were able to remove the requirement of a training set by now requiring a seed training set. So this would be very few samples, tens of samples as opposed to hundreds or thousands of samples. And we would again learn a property alignment, learn a blocking key. These may not be as good, but they're good enough that when we get to this stage, we get some signal. And then we have this self-supervision kind of loop, where we take those signals and then we try to relearn the similarity function, and then we get, same as links. And, we do this in some cycles, and then we get a final final set of same as links that works quite well. So that's the intuition. There are questions I can go into more details, but we have a paper on this that describes the process. And then finally, we lifted that up even more. When we were like, let's try to get this unsupervised, because where does the seed set come from, right? I want to just say a little bit about why the seed set is problematic, why that's not an artificial problem. The reason is that you have m nodes and n nodes, right? If you randomly sample the pairs, OMN, let's say you have the pairs OMN, you randomly sample some pairs and you label them. The problem is that there's a heavy skew. Most of the samples in O of MN will be negative, right? They will be non-duplicates. If I give you 1,000 companies in one data set and 1,000 companies in another data set, and you randomly sample a pair, you're going to get a non-duplicate, right? You're not going to get a duplicate. So random sampling does not work for this, unlike many other labeling problems. So even getting a seed set could be problematic. And it could be that if you try to do this in a way that is non-random, you might be biased. You might pick up the easy samples, right? So this is in itself a harder problem. Getting the seed set turned out to be a harder problem. And what we instead proposed was that we should have an automatic training set generator. So the idea is you give me the two IDF data sets, and I had this special thing called a training set generator that would try to come up with its own noisy seed training set of duplicates and non-duplicates. And everyone thought that if it's a noisy seed set, I mean, first it's small, it's a seed set, then it's noisy, because this can't be guaranteed to be perfect. It's unsupervised, right? How could this possibly work? Wouldn't the noise dominate at some point? But that's where, the system that we proposed was really able to cycle around this and get rid of the noise. So there are lots of details in these algorithms, that were published over the years, but we were able to find a way to get rid of the noise and get a lot of signal. And we tried it on many, many domains, in a journal article that I put out in 2015 and then built upon in later years. We tried on 6 or 7 different domains that were not easy. There was, many of the entities had no links to Wikipedia at all. They were all long tail entities. We were able to get a pretty good signal from that, near supervised performance by the end of it. So that was very promising. And then finally, we were even able to show that we could move many of those algorithms into MapReduce. So you can run this on very cheap commodity hardware. You don't need GPUs or anything of that sort. Although you could, if you wanted a similarity in embedding space, you could apply the GPU and learn the embedding and so on. So you could get scale over there also. But overall, this pairwise problem, we could move it to MapReduce. And then we found that you could get these links pretty much by just running a standard cloud architecture, very low cost because of the MapReduce. And that was very encouraging to do that. And then we evaluated on DBpedia, which contained all the entities in Wikipedia with their properties, against Freebase, a version of which is available. And that was how we did the scalability evaluation with millions of nodes in each of the knowledge graphs. And it ran very fast. Less than $50 to $100 of cost in total to get those links. So industry got very excited by that. Even today, I advise several startups who want to do this for their domains. And there's no one system that is available that can do it, but this architecture works. And you can apply it to many domains and startups to get links for less than $100 if you can pull it off. All right, so I just have a couple more slides, and then I know we have a panel coming up, but I want to close out with the high-level vision that Vinay mentioned at the beginning, which is entity resolution enough? And it turns out that it really isn't enough. And this is the slide that I hope I can give you, and that maybe will communicate to you what a KG ecosystem looks like, because we often don't talk about the individual components and how they tie together, right? And I like to point to this because it not only tells you what the different problems are and in what order they happen, but also what the communities are, right? Where the papers in all these problems tend to get published by and large. So, if you want to design an ontology, let's say that you have an unusual data set, Let's say you're trying to track dark money flows across the financial ecosystem, which is a very real problem. You want to design a domain for that, an ontology for that. That kind of thing really comes from the semantic web. You have things like the web ontology language or OWL. You have RDF, it builds on RDF. I introduced RDF earlier. All of that has been developed in the semantic web. The specifications are available, the languages, models. The Wikidata model is one rare example of something that wasn't developed in the semantic web, but there's a huge part of the semantic web that deals with Wikidata. So that's also an alternate model. But a lot of times you can just download the domain model also. It's, or you may not need it. It may already exist. But, and these are not all compulsory steps. This is just if you're really starting from the very beginning. But there's a domain model. You also have the raw data. It could be social media, reviews, text, articles, what have you, right? So that's your raw data. It could be tables. We've also seen tables that can be converted into knowledge graphs. At that point, you have KG construction. You need to extract information, right? So extract relations, extract entities, extract events. You need to link those to Wikidata, to DBpedia, and that's the entity linking. You need to link pronouns and anaphora, that's co-reference resolution. It also tends to fall here. At that point, you have a KG, right? This is a rough KG. It may be incomplete. If you do KG construction at scale, document by document, you're going to have the same entity extracted from many documents. And this is the entity resolution problem, right? Sometimes you want to link to a pre-existing knowledge graph, as we just saw. You also want to train embeddings on the knowledge graph. You might want to do probabilistic soft logic to infer missing relations and so on. But you want to complete the knowledge graph. You want to identify the knowledge graph. This is where a lot of the work is happening in KDD, in machine learning, core machine learning, representation learning, more recently also in NLP. And then finally, there's this very important component, which is knowledge graph access. Where do you store the knowledge graph? How do you query the knowledge graph? For those of you who are maybe working in the industry or wishing to go into industry, Amazon Neptune, great cloud product that can be used for this, but there are several others, Neo4j, and so on. And then, all your end user applications will be working with this knowledge graph. And then, you might have visualization and other things on top of this. So this is a complete ecosystem. It's a very big ecosystem. And this is my very last slide. But I just want to give you some avenues for future research, especially for PhD students out there. And I think the biggest avenue is we still don't really have, except in very big companies, a fully end-to-end scalable deployment of a complete KG pipeline, where you have state-of-the-art algorithms for IE, for ER, for knowledge graph representation learning. The individual algorithms exist. How do we put them all together, right? And get that final product? I think we really need that. We don't have that right now. How do we visualize KGs and interactively manipulate them, add information, remove information? We still don't have good visual tools for a lot of those steps. We saw in the previous talk, long tail versus short tail. This problem exists throughout the spectrum, including in ER. Systems level versus reductionist, right? We can try to improve performance on one problem. How do we improve performance across the board, right? So I might say, okay, I've improved IE, I'm extracting relations with 10% more F1. That's good. Does that 10% more F1 give me 10% more performance down the line, right? Or does it give me 2% more performance? Does it give me 20% more performance? We don't know, because noise is not random, right? So we don't know. No one is really evaluated at the systems level. This is a huge problem. Easy to use open source software development. We've made huge progress as a community. We're still not there yet. We need more open source tools. And then finally, improving performance and speed. I mean, that's always a goal, right? We want to keep improving. But I would say that these are the bigger problems. We already have good performance and speed, but we need to address these bigger problems now. We can't just wait to get 100% performance before we get to the bigger problems. So with that, I will close out and looking forward to more discussion.
Thank you, Mayank, for excellent presentation. We have about 10 minutes, 11 minutes left for discussion. Naren, which question do you want to go with first?
Sure. So Mayank and Laurel, both were very good talks and very practical. There are two questions for Laurel on the Zoom. So Laurel, how do we find similar long tail entities can it be done through reasoning, or will it need some NLP tasks or techniques?
And do you mean by similar, like the entity resolution type of matching, or is that what you guys mean by similar?
Yes, I think that is the semantic of similar.
Yeah, that's actually a really interesting question, because as it stands, you would have to, the similarity would be based mainly on like the types and knowledge graph relationships. If you had enough, I think, knowledge graph relationships that would fairly uniquely identify an entity, I think you could get away with it. But that's actually, yeah, it would be a little harder, I think, with the way that bootleg was sort of set up. There's been a recent trend in these sort of entity encoding methods that actually uses more NLP methods with BERT, although they're a little sneakier with what they actually feed into the text. And so I think for that, they're relying on things like entity descriptions, still with types and stuff, to encode an entity via transformer. And I think that would probably do a little better. But again, it would all rely on what structural resources you have available. And if you have a really sparse knowledge graph, or you don't have a description, then you're in for a little bit of a harder time.
Okay, thank you. And there's one more question for you. Any insights on the expressiveness and amount of knowledge that is needed for reasoning over patterns to obtain the sweet spot of high accuracy and low manual effort?
Yeah, no, that's another really good question. And there's a subtle part to disambiguation, which is all about these candidate lists that I talked about, in terms of what possible entities that you could disambiguate for a mention, and how the relevance, the importance of your structural patterns, your types and knowledge graphs, is their ability to discriminate within that candidate list. So if all your candidates have the exact same type, it's actually going to be less useful of a resource. And so there's some sort of nuance that you need when you're examining the kinds of candidates and the resources that you have there. We found that for English, and Wikidata is actually very useful. That actually is a fairly high quality knowledge base, and their relationships and types were pretty good for our use case. We've been doing some work in medical text, and that's a whole other ball game. Their types aren't very useful. They're very, like, they have a type that's called a finding, which like fits, basically every entity in the knowledge, but so it's a very different ball game. And some of the stuff we've been trying to do have actually been to try to transfer Wikidata knowledge bases into this medical domain over the relevant subsets, because it's a much higher quality knowledge base. So it's an open problem, I think. And some of it is sort of manually understanding your data, and understanding what other sources you can pull from, all trying to keep it as sort of less or as unmanual as possible.
Okay, thank you. And there's a question now for Mayank about his vision of the ENS, which is quite appealing.
Yeah,
so Mayank,
I'm reading the question. Okay.
Okay.
Or sorry, do you want to?
No, go ahead, please. Please go ahead.
Okay. Yeah, I think I would say the most it's the best application that I have found is in e-commerce. So I've had the good fortune of working with several big companies on e-commerce, and the Amazon product graph, I think, is really like an ENS, because they have so many different products, inside the product graph. And there are third party, there's not just one person who is selling the product, right? So if you, in some cases you do, but if the product might be the same, but you might have multiple sellers of that, right? And Amazon itself might be selling. And then there's a higher level, which is the product category, right? So the specific product with the product number, that might be specific. Like, there's a very serial number of a product, which is a single instance that uniquely identifies the product. But inside the Amazon product graph, what they have technically are product categories, right? For which there may be many instances, like 1,000 units, SKUs, whatever, that terminology. So that is a big use case. They're calling it the Amazon product graph. They don't like to call it a knowledge graph, I think, because they have this broader vision. I haven't seen the terminology ENS catch on a lot, but the definition is very similar to to the one I proposed, which is sort of like a knowledge graph version of a data warehouse. Also in several other domains, that are related to people, where they have lots of customers, they are also trying to ontologize those databases and make it more of a knowledge graph. And in some cases, I know that they are trying to link them to things like social media profiles and, which is kind of like linking to Wikidata, but slightly different, right? Because, the person is usually not a famous person, but they are all over the web, right? They have all these different things on the web, and sometimes you explicitly give them the information. You give them the LinkedIn profile and the social media profile, or you sign in with LinkedIn. But in other cases, you may be in other places on the web that you're not giving them access to, or that you're not explicitly stating, and they still want to link to it. They want to try to understand you better.
So I have a question for both of you, and this is on the use of the term unsupervised or self-supervised, because your unsupervised and self-supervised techniques are really riding on Wikidata or Wikipedia, which somebody has manually curated, right?
Yes.
If you go into a domain where entities you are dealing with, they are not in Wikipedia, then how does your self-supervised or unsupervised technique work?
Sure, I can go first. So in the architecture that I showed, the self-supervised technique that we use is actually based on weak supervision rather than on distant supervision. So the training set generator that you saw, it just uses the two inputs. It does not actually use Wikidata or the external knowledge graph, although we can integrate that also. Both can be used, in the same architecture. But we try to generate training samples just from the inputs, not from the Wikipedia or Wikidata external source. So in theory, we have shown that it works on, or even in practice, we have shown it does work on knowledge graphs that are not linked to Wikipedia or Wikidata. But we are linking between the knowledge graphs, so we're not trying to link to the web. We're linking between two knowledge graphs is maybe the difference.
Okay, Lauren.
Yeah, no, that's that's a tricky question, especially when you're dealing with non-English sort of sources. Weak labeling is a common approach that I think some people take. I will say that defining a lot of label functions for for entity resolution, it can be a little tricky because you're not dealing with like a binary classification task, right? It's a complex task. I think some of the successes that we've seen have actually been leaning more heavily on how can you leverage the knowledge that you have learned over this Wikipedia data to do some sort of more transfer learning approaches. And so maybe you do need some manual labels, but over a much smaller subset of data. So for example, if you're a company and want to train a model to disambiguate product entities, conceivably you could label a small subset of data and then transfer some of the knowledge from our Wikipedia model to help you sort of overcome the limited label regimes. I also think some methods in augmentation could be useful as well, and sort of where you synthetically generate data, although that's a very open question that I've sort of just been marginally thinking about here and there. But yeah, no, it's a relevant problem, especially in industry.
Well, there is this question, is a field name an entity? And I'd say no, field name is a predicate, right? Because our data model is subject, predicate, object, right? So
no, let me actually try to, it's a very good question actually, even though it seems like a simple question, but it turns out it's a, so my answer to you would be that at least in the semantic web, the way that we answer this question is that in the ontology, is that defined as a literal or not? So for example, if I have a date, so if a date is defined as a literal, then that would not be an entity. That is what we would consider a literal or an attribute sometimes. That's another word. But if you have a person's name and the person has a type in the ontology, then we would consider the person, whether it occurs in the subject or the object, as an entity. So at least in the RDF world, URIs are generally used to refer to entities, and literals are used to refer to non-entities, to fields or to auxiliary information, to attributes. And so it can depend on your ontology. If you define your ontology a certain way, then suddenly the URI could become a literal or vice versa. So it depends on the ontology is what I would say.
Okay. Okay. Mike, did you have anything to say? Add here?
No.
Okay. So I thought this idea of using types to kind of propagate things from highly occurring entities to less frequently occurring entities. I mean, I thought that was pretty cool, and part of me was thinking that, oh, this is what classical knowledge-based systems do. That's how the inference is supposed to work. But the interesting thing that you have in your architecture is that some of the calculations you are doing using embeddings, like automatic embeddings, but you still need somebody to tell you what the right relations are, right? So I mean, that part is still, again, I don't know where you are getting your relations from. Are they manually engineered, or are they automatically engineered, or?
Yeah, so these are also from Wikidata. So we automatically extract them. We do a little filtering so that if you have a relationship that exists, one time in our data set, it's not going to be that helpful for us. So yeah, we and then we just sort of throw them at the model. We give them sort of all relationships, and the hope is that it can learn to reason over which ones are the best one given the context of the sentence. But it's not always perfect, right?
But I think if you got your relations from Wikidata, then they are engineered, right? Because Wikidata is
sure, in that case, since yeah,
it's an engineered ontology. All right.
So Laurel, sorry, are you out of time?
Yes, we are 1 minute over time.
Fine, I will follow up later.
So I'd really like to thank both Mayank and Laurel for joining us and sharing with us their perspective. And a really great vision, Mayank, for this global entity system and this idea of.
By the way, I'm very happy you ended the session over here, because I don't think I want to criticize TVL. Well, TVL is Tim Berners-Lee.
I mean, I think that recent comment that somebody posted in the chat is, I think, a little bit orthogonal to the substance and technical issues we are addressing here. And I think in the course, we've tried to stay focused on solving the real problems, actual problems. And I think both of things that you guys presented, they are actually solving real problems, right? And the big visions, they will happen or will not happen. Time is the best test, right? We cannot predict anything. But regardless of that, I'm really grateful that you guys took time out of your busy schedules and presented here. Thank you very much, and we will stay in touch. And
thank you.
Thank you. Thanks to both of you.
Appreciate it.
Yeah, and as far as the course is concerned, we will continue next week. And next week, our focus is going to be on how to create a knowledge graph from unstructured text. So we'll see you next week. Thank you, and bye for now.
Bye-bye.